You think the coast is where evolution slows down. The interior is where the pressure is, the forest, the competition, the arms race between body plans that has been running for 25 million years. The coast is the edge, the margin, the place organisms wash up when they can't compete where it counts. That assumption is wrong. And on Arthronia, at the edge of the Chitophilian interior, where the blooming mangrove forests descend into the tidal zone, the organisms that moved to the margin didn't escape pressure. They found the one pressure the interior never had. The question isn't why they went to the coast. The question is what the coast did to them once they arrived. On Earth, the mangrove coastline is one of the most hostile biomes a terrestrial arthropod can enter. Salt, tidal flooding, anaerobic mud, tannin-saturated leaf litter with a nitrogen content so low that most detritivores cannot extract sufficient energy from it to reproduce. Research on mangrove leaf decomposition confirms what the biology predicts. High tannin species like Rhizophora suppress microbial activity, resist detritivore digestion, and decompose at a fraction of the rate of terrestrial forest litter. On Earth, arthropods at the mangrove margin are specialists of necessity, organisms forced into a difficult habitat because they lost in the interior. The biology is clear. Moving to the coast is a retreat. Now consider this. On Arthronia, at 25 million years post-seeding, the aphid lineage of Chitophilia reaches the coast, not retreating, radiating, following the blooming mangrove expansion outward as the forest pushes into new ground. The same tidal hostility, the same tannin chemistry, the same salt and flood and anaerobic mud, different outcome, because one variable changed. What happens when an organism built for pressure enters a biome that has no competition, and the only thing standing between it and total resource dominance is the chemistry of the environment itself? Convergent evolution, the independent arrival at the same solution under the same pressure, is one of the most documented patterns in evolutionary biology. It is not a coincidence, it is a mechanism. The mangrove tree solved salt toxicity, tidal flooding, and root zone anoxia through a suite of adaptations: hydrophobic cuticle layers to prevent osmotic dehydration, specialized salt glands to excrete excess ions, pneumatophores and prop roots that breach the anaerobic mud to access oxygen. These solutions evolved independently across at least 15 mangrove lineages on Earth. The problem space was fixed. The engineering solutions converged. On Arthronia, at 25 million years post-seeding, the first aphid lineage to follow the blooming mangrove into the tidal zone encounters the identical problem space. The result: mangrove root aphid body length, 40 to 55 centimeters. Weight, 1.2 to 2.0 kilograms. Descended from the tree aphid lineage of the Chitophilian interior, the same elongated stylet, the same siphuncular secretion glands, the same 6-limb body plan, redesigned. Its exoskeleton surface carries a waxy, hydrophobic cuticle that functions identically to the mangrove tree's own salt barrier. Convergent solution, different kingdom, same physics. Its spiracles, the valve-controlled breathing pores running along the sides of every arthropod body, have evolved a complete seal mechanism, documented in real insect physiology as muscular closer apparatus controlled by the central nervous system. In Earth, insects, spiracles close to prevent water loss. In mangrove root aphid, the closure is extended and reinforced. The animal can hold its spiracles sealed for up to 40 minutes during tidal submersion and reopen them precisely as the waterline drops. Its siphunculæ, the paired secretion organs inherited from tree aphid ancestors, have shifted function. They now excrete salt, concentrating and expelling excess ions absorbed during feeding on submerged roots. Salt glands, derived from secretion organs. The mangrove tree's solution, arrived at again, in an arthropod. The mangrove root aphid lineage predates the blooming mangrove forest's full coastal expansion by approximately 400,000 years. It was already adapted for a habitat that did not yet fully exist. The mangrove specialist solved the coast, but the raptor ant legion cannot follow it there. The coastline is flooded, unstable, and salt-hostile to ground-dwelling insects. For the first time in the Chitophilian fossil record, a food source exists that the raptor ant cannot reach. So who fills the space between the mangrove specialist and the interior, and what happens when something does? What I describe next is extrapolation from known evolutionary biology, stated explicitly as speculation on Arthronia, grounded in documented mechanisms from Earth. In Earth ecosystems, heavy metal tolerance in organisms follows 4 documented strategies: metal exclusion at the cell membrane, active storage in specific tissue compartments, immobilization through binding proteins, and reactive oxygen species detoxification. All 4 strategies have been observed in insects exposed to metal-contaminated environments. At 26.5 million years post-seeding, a subpopulation of grass aphids, interior generalists, not coastal, is repeatedly exposed to a different Chitophilian problem, the acid fern swamp zones. Iron-saturated, acidic water pooled between peat layers, a toxic dead zone for most organisms in the ecosystem. Most died, a minority survived. The rust aphid, body length 30 to 38 centimeters, compact, low profile, and visually unmistakable. Its exoskeleton is rust orange to dark reddish brown, not pigmentation, iron oxide, mineralized into the cuticle surface layer. The animal is actively sequestering excess iron out of its gut and depositing it into its shell. The byproduct of its detoxification strategy is biological armor. Its gut microbiome produces organic acids, analogous to oxalic and malic acid, that chelate iron and heavy metals before they reach sensitive tissues. Its gut lining is thickened, acid-resistant. Its stylet has evolved from the ancestral piercing design into a tri-lobed, boring rostrum, capable of drilling into the rhizome base of the acid fern, the toughest plant tissue in the ecosystem. And its sipunculi no longer secrete sticky compounds. They store acid. Rust aphid eats the acid of the acid fern, processes it through a specialized gut, and weaponizes the output through its sipuncular organs. An animal that has integrated its food source's toxin into its own defense system. This, on Arthronia, where the acid fern zones continue to expand, is not a fringe adaptation. It is total resource capture of a toxic biome that nothing else can enter. 2 food sources, 2 locked doors, both inaccessible to the most dominant organism in Chitophilia. But here is what the biology predicts will happen next, and it begins with the animal that eats mud. Detritivory, the consumption and processing of dead organic matter, is the metabolic foundation of every terrestrial ecosystem. Without it, nutrient cycling stops. Litter accumulates. The system collapses. In mangrove ecosystems on Earth, detritivore function is constrained by the chemistry I described, high tannin, low nitrogen leaf litter, that most organisms cannot efficiently digest. The ecological consequence is documented. Mangrove detritus decomposes significantly slower than terrestrial forest litter, and the specialized microbes and invertebrates that process it are limited in diversity and biomass. At 27 million years post-seeding, on Arthronia, this is speculation, A subpopulation of mangrove root aphid descends from the prop roots to the tidal mud beneath. The mud aphid. Body length 55 to 70 centimeters. Weight 2.8 to 4.5 kilograms. The largest body plan produced by the Chitophilian aphid radiation so far, and the flattest. Dramatically dorso-ventrally compressed, a low drag profile for moving through shallow tidal mud. Its 6 legs have broadened into wide paddle-like appendages with stiff marginal bristles, not for swimming. For walking through mud and shallow water simultaneously. Its stylet is gone. In its place, a broad spade-shaped scooping rostrum used to shovel and compress decomposing leaf matter, mangrove bark fragments, and organic sludge directly into its mouth. A complete abandonment of fluid feeding. A dietary transition documented in earth invertebrate lineages as major evolutionary shifts, from phloem sap to structural carbohydrates. Its gut has expanded to occupy nearly 60% of the abdominal volume, running a tiered fermentation system that processes tannin-rich mangrove detritus through staged acidic breakdown before the nitrogen-poor residue reaches absorption tissue. Its ventral surface is partially permeable. Dissolved nutrients from the waterlogged mud absorb passively through the belly surface while the animal feeds. It eats, it absorbs, simultaneously. Now consider what mud aphid represents for the raptor ant legion. Mangrove root. Aphid is inaccessible. The mangrove root system is flooded and salt hostile to ground-dwelling insects. Rust aphid is chemically locked. Its acid spray defense and toxic habitat prevent ant raiding. But mud aphid is large, slow, and defenseless. It cannot escape across mud efficiently, and it lives in the intertidal zone, accessible on foot during low tide. The raptor ant can reach it, but only during a window of approximately 90 minutes per tidal cycle. The colony has never encountered a food source with a disappearing floor. Remove the raptor ant from the interior, and the food web destabilizes. This has been established. The colony's role as apex harvester and trophic regulator is not incidental to Chitophilia. It is structural. The ecosystem was shaped by its presence. At 27 million years post-seeding, the colony reaches the coast, not by decision. The pheromone gradient tells it to press forward. It presses forward. It always does. A raiding party enters the intertidal zone during low tide. It reaches a mud aphid colony. It feeds. The tide begins to rise. Some workers are lost. The survivors return carrying something that has no precedent in the raptor ant's pheromone library. The chemical signature of mud aphid honeydew mixed with salt water embedded in their cuticle. Back in the colony, other workers begin following that scent trail back toward the coast. Not commanded, not sanctioned. Following a gradient the colony did not place. A column of workers moving toward the water, unprompted. A system does not decide to move toward the coast. It follows the gradient. The gradient has no awareness of what it is pulling the system toward. 40 million years of selection pressure produced a colony that cannot evaluate a decision, only follow a signal. And now the signal points somewhere the colony's architecture was never built to handle. The floor disappears, the tide returns, the gradient remains. What is the difference between a system that is adapting and a system that is simply following the last signal it received into terrain it was never designed to survive? The raptor ant colony has not lost a territorial war in the 800,000 years of the Chitophilian fossil record. It is not losing one now. What is happening is smaller than a war, quieter. A column of workers at the tree line, responding to a chemical trace embedded in a returning worker's cuticle, moving toward water. Selection pressure does not warn a system before it introduces a new condition. It introduces the condition. The system responds. The response that survives is the adaptation. The response that doesn't survive is the fossil record. Arthronia is still writing the record. The last worker at the colony edge pauses at the mangrove root line. The water is rising. The pheromone gradient still points forward, into the flood. The worker follows it 3 body lengths into the salt water. Then it stops. It does not turn around. It waits. The tide rises over it. The colony, in the interior, does not know it is gone. It was never tracking it.